evening. My name is Steven Reiner. I'm with the Alan Alda Center for Communicating Science at Stony Brook University, and this is Science on Tap. Tonight we're going to go driving on Mars. And as we all know, Mars is the fourth rock from the sun, has been an object of fascination for all of us in different ways for many, many, many years, for centuries in fact. It's been the subject of excellent science fiction and the subject of terrible science fiction movies. And we've learned a lot about Mars, and we're about to learn a lot more tonight from our guest, Scott McLennan, who is a professor of geosciences at Stony Brook University and one of the people who is out at the Jet Propulsion Laboratory in California working with the Mars rovers, examining the surface of Mars to find out that answer to that now age-old question: was there ever, or can there possibly be, life on Mars? So Scott, right now we're going to start with that moment about 18 months ago when the rover first descended and landed on the red planet. I'd like you to walk us through that moment and narrate this video, which shows us both in a computer animation and in real time what went on 18 months ago.
We're going to pick this up just as the rover that's inside its heat shield has entered the atmosphere, going from about something over 10,000 miles an hour to, 1,000 miles an hour. It deploys a supersonic parachute, and of course if it was Earth with our atmosphere, that would take you to the surface fairly gently, but on Mars it can't do that. So as you mentioned, we're now going into a split screen. At the bottom of the rover there's a camera that looks straight down called Marty, and as the heat shield is released, you can start to see the surface of Mars. So the one on the right is a camera that's taking images. I think it's roughly 10 images per second. And on the left it's the animation based on what's called the telemetry, or the radio signals from the rover that's reconstructed.
So we're looking at the surface of Mars.
That's right. Those dark things are a set of sand dunes that are just fairly close to the landing site. So now we've gone over from the parachute to powered descent, so the rockets have taken over. And this slows us down from about 200 miles an hour down to something like, it's like 2 miles an hour. It gets very, very slow. And you can see the dust getting kicked up. And about 60 feet above the surface, we deploy this amazing thing called the sky crane that puts the rover down. And you can see in the picture on the right, in the upper left-hand corner, the wheel is deployed out. So it locks into place, slowly brings it down to the surface. As I said, it's kicking up a bit of dust. And then the rover touches down. The sky crane recognizes that, it cuts the lines, and then off it goes, hopefully far enough away that the explosion doesn't do any damage, and it didn't. During the landing, we're a team of over 400 scientists and some comparable number of engineers. And at the landing, we saw the tones coming back from the rover as it was working its way through the atmosphere, saying that this had worked and that had worked. And each time, of course, the cheers go up.
And if you look here, what we have on this table right in front of us is a scale model of Curiosity. What is the scale of this compared to the real thing?
Okay, so this is a little over 7 feet high, and then everything scales to that. I guess the easiest way to give it a general sense of the scale is that this is a 1-to-1 scale model of the wheel. So that's what scales it up. So that gives you a sense.
So that's one of these little...
That's one of these, fairly big things now, but yeah.
Okay, tell us a little bit about Curiosity. Tell us what it is, what's on it, and what it's supposed to do. Why is it there?
It's a robotic explorer. It's different from anything we've sent before because it has an internal laboratory that can make measurements on rocks that we've never been able to do before. And its purpose is to look for a geological environment that would have been habitable, which means that that if life was there, it could have survived and thrived at that location.
All right, well, before we get into discussing what this is doing today, I think it's good to understand what preceded this.
Okay.
So we're going to bring out this little feller.
So this is a scaled model. So they're both 1 to 10, scale of 1 to 10. And this is the scale of the Opportunity rover, which is roughly 1/5 the mass, 1/5 the size. It looks a little bit bigger because the solar panels stretch it out a bit. But this rover is, as I said, this one weighs just under a metric ton. This one weighs about 1/5 that, so it's about 200, a little under 200 kilograms.
And Opportunity landed in 2004.
2004, January, that's right.
With a partner.
With a partner, Spirit.
Simultaneously, but very close. What was the work of Opportunity and Spirit? Why were they there?
So Spirit and Opportunity, they were sent out, again, as geological explorers, nowhere near as sophisticated as Curiosity, but their job was more of this follow the water idea.
So before you look for life, you want to look for water. Exactly. Why?
You know, you can always argue that life is different on another planet than it is here, but if that's the case, there's no way of searching for that because there's no model, there's no understanding. So the presumption is always that life on Mars will have some similarity to Earth, and on Earth, the one thing that ties it all together is that it all requires water. There's sort of this inside joke on Mars exploration, which is that every Mars mission has to discover water for the first time. And there's some truth to that, but it's actually a bit more sophisticated than that, in that what this is looking for is ancient geology in which water was active. And we have a pretty good understanding about how to look for ancient geological formations in which life might have existed and then would be preserved. It's a much harder thing to go and look for current life because we don't know what to look for, we don't know where to go.
Now this took a very, very long journey to get to Mars, and how long was it expected to do its work on Mars?
Its life expectancy was quoted as 90 Martian days, 90 sols, which is just a little bit longer than an Earth day. And I think most people felt that it would last a little bit longer than that, but that's what it was guaranteed for. That's what was, if it had done that, it would have been completely successful. So it was 90 days, and now it's, in the case of Opportunity, it's well over 3,000. So it's done an extraordinary job of
So
surviving.
it's kind of the Martian version of Hanukkah, basically. It was somewhat of a miracle. The oil was supposed to burn for 9 days, and it kept on going. The oil's still burning on Mars.
These are just, I mean, superbly built robots and superbly built spacecraft. The other thing that's happened is that over 10 years, it's, you know, think of how many, almost every day you have to send up a set of commands in a computer program, and the chances of making mistakes, you know, over 3,000 times is pretty, you know, one would think would be pretty high. But very, very few mistakes have been made. So these have been superbly managed rovers. They've been superbly managed spacecraft.
Now Spirit wasn't so lucky.
Spirit wasn't so lucky, although it did last nearly 2,000 sols, and it finally got done in by, it got caught in a sand trap. It was unexpected, and it drove into some very, very soft material, and it just couldn't get out in time for the winter that was coming on. And the way this is set up is that in the winter, we tilt these into the sun, and Spirit was more prone to the prowling because it was at a further southern latitude. So it really had to be 15 degrees into the sun for the winter, but it got stuck, and in fact it was stuck a couple of degrees away from the sun. They got very close to getting it out before the winter set in, but they just couldn't quite get it out, and then it just didn't survive that winter, and we lost it.
So what are Opportunity's accomplishments? And I understand that Opportunity took some selfies, took some pictures of itself while it was there.
It has. I think we're seeing one.
Okay, right over there.
And we're seeing what the third thing that really has made the difference with these rovers. But this is after some period of time, and you can see that the solar panels are all covered in this dust. And everybody thought that this would be a process that would just accumulate over time, and over time we would just stop losing the solar input, and that they would just slowly run out of power. This is a more recent selfie. And this one was after what we call a dust clearing event. And basically it's a wind gust. And the wind gust has come along and basically blown off that dust. And we now get power that's approaching what we had on the first day of the mission.
And no little green men with a dust cloth? No, for sure. Okay, so this is the wind. This is the wind. Okay, so now that it can continue to function well, what is it seeing? What has it seen?
Okay, so Opportunity has really had 2 lives, 2 missions. This is a map looking down from orbit. It's traversed over 35 kilometers now. And you can see there's a very large crater in the bottom right-hand corner, Endeavour crater. But before it got to there, it went across the light-toned plains. And this is where we found these deposits that were formed by wind activity, but that had groundwater that every once in a while seeped up and came to the surface. So we spent a long time crossing over that, many times thinking we were setting goals that we would never reach. And the last goal we set was this large crater. And one of the things that's well understood is that when you have a meteorite impact crater, you generate an enormous amount of heat. And that heat sets up convection cells. So if there's subsurface water, that subsurface water will start to move through the subsurface, not unlike this type of thing you would see at Yellowstone Park, okay, where Old Faithful is, that kind of hot water environment, and that will come to the surface. And on Earth, that's not just habitable, but that is a place where you have incredibly diverse microorganisms that thrive there.
Well, of course, today Mars and the Earth couldn't be more different.
Right.
Average temperature on Mars is minus 80-something degree Fahrenheit. But if you go back 3-4 billion years ago, these planets were fairly similar.
We think they were much more similar. Right now, the atmosphere of Mars is about 5 or 6 1,000ths of the density of our atmosphere. Very, very little atmosphere. Just enough so that you have to have so much trouble landing on it. But in any case, it has very little atmosphere, and if you have liquid water on the surface now, it just wouldn't survive. It would just evaporate away, and ice tends to sublimate away. So earlier on, it's thought we had much more atmosphere. That atmosphere probably was very rich in carbon dioxide, because you need carbon dioxide to give you the greenhouse effect in order to warm the atmosphere enough, because this is much further away from the sun. And so the idea is that you had a much thicker atmosphere that was fairly rich in carbon dioxide that allowed for liquid water to form and to flow on the surface. And there's lots of geological evidence of that too.
So why did Mars, I know no one knows the exact answer, but why did Mars go one way and the Earth the other way?
There's a couple of reasons that seem pretty likely. So one idea is that you have meteorite impacts that hit the surface, and they slowly erode away the atmosphere and the water. Another thing is that Mars, early in its history, we know by looking at rocks, what are called Martian meteorites that have made their way to Earth, we know that Mars had a magnetic field, just like the Earth. And Earth's magnetic field protects us from the solar winds that would tend to erode away our atmosphere. So at some point at around 3.5 billion years or so on Mars, it lost its magnetic field. That seems to have shut down. And once it did that, then it was very susceptible to these solar winds that would erode away the atmosphere.
So that state of knowledge, what we knew about Mars up until the time that this started doing its work, what were the big questions that this extraordinary device had to start answering?
So
and how did it start doing it with all these?
Two major things. One is that both by the work of the Spirit and Opportunity rovers and by all of the orbiting spacecraft that have gone to Mars by both the United States and the Europeans, we have come up with this sort of paradigm that there was a change in Martian environments at the surface. Early on, we had this sort of so-called warm and wet environment, and then there was a sudden change that we essentially desiccated the planet, dried it out, and when we dried it out, we caused what waters were there to be much more acidic than they are on Earth, typically, and what we thought earlier in Mars history. So one thing is we wanted to test that model, to test whether or not that kind of an evolution took place by going onto the ground and looking at the rocks and minerals that are preserved. The second thing is that the Spirit and Opportunity rover did indeed, both rovers, very successfully identified geological environments in the ancient past of Mars that we think would be habitable. So then we have these habitable geological environments, but then the next question is within that environment, can we find, for example, the energy sources that life needs? Can we find the carbon sources? Can we find the sources of all the other elements that we know life on Earth requires? Things like hydrogen, nitrogen, carbon, phosphorus, sulfur. So are the building blocks there, and is the energy there? Can we come up with the energy?
And those are the questions.
That's the questions that this was doing.
Okay, so let's now talk about the work that this is doing. Right. Where do we start with that?
Once we landed, we knew we had to go somewhere to get all the instruments set up, make sure they were all working. And from orbit, we knew that there had been this ancient river system. And so the idea is that we would go to sort of the furthest reaches of that river system, and it turned out to be an extraordinarily exciting place because the rocks that were preserved at the end of that river system included a lake. So these are lake deposits, and on Earth, biological organic material both can live in a lake environment, and just as importantly, they can be preserved in a lake deposit. So this is a place where we really put to use the tools of the Curiosity rover.
Now, what are some of the tools here?
Okay, so the instruments are basically divided into 4 types. This is the mast, and this is what we call remote sensing. So we have color cameras, and we also have a laser instrument that will put laser shots onto the rock from which they can measure chemical composition on sort of millimeter-sized areas. So we use this to find things. The arm, then, this is what we call the contact instruments. And on here we have one instrument that will measure the chemical composition of a surface, another instrument that will brush off the dusty surface, because as we saw on Opportunity, things tend to get dusty on Mars, so you can brush that dust off. And then a camera that is like a hand lens, like a loop that you would use by a jeweler, about that kind of capability. And then really what's really special about this, and completely different than Spirit and Opportunity, has a drill. And the drill can drill up to about 5 or 6 centimeters into the rock. It produces powder that then gets delivered up into a holding container within the arm. And then that can then turn back and then deliver samples. I'll put the mask down so you can see. Deliver samples to 2 instruments that are inside the rover. And one of those instruments is what's called a gas chromatograph mass spectrometer. And that allows you to look at isotopes of these critical elements: hydrogen, oxygen, carbon, and their abundances and their species. The type, whether it's carbon dioxide versus carbon, whether it's methane versus this or that. And then the other instrument that's inside is what's called an X-ray diffraction instrument, and that's sort of the gold standard on Earth for determining the mineralogy of rocks of rocks. So it delivers it to both, and then they do their thing inside the rover.
Now, from what I understand, this wasn't even assumed to be the most promising area. That the rover is still on its way to the point of its mission.
That's right.
And it's taking so long to get there because it's been so fascinating and so successful. So talk a little bit about that.
So the promised land is about 8 kilometers from the landing site as the crow flies. And this is showing where we went. So in the upper right-hand corner, you can see the little jog off to the east. And on the internet, of course, as soon as we landed, people were saying, "Why are you going the wrong way?" And we went there because of this geological formation that we've got so interested in. That's Yellowknife Bay, and we spent so much time there. The white track now is showing the route to Mount Sharp. And it's in Mount Sharp where from orbit we see these mineralogical transformations that we ultimately want to go and evaluate and study.
Okay, now we have another picture which is really remarkable because you can see the tracks of the rover.
And then every once in a while you'll see a little circle. The 4 corner wheels can be independently steered. Each one can be steered separately.
And now we're actually seeing the rover on the surface of Mars.
That's right. And we're up against this region called Mount Remarkable, and it's it's
great remarkable.
All great names. In a map region called the Kimberleys, which is named after the Kimberleys in northwestern Australia.
Which is a diamond mining region, so it's named after a carbon region.
That's right, carbon in another form. Yes, so we hope. And we're now looking, this is from the navigational cameras, the black and white cameras, looking into Mount Remarkable and looking into this region that when I was in Pasadena last week, we're just kind of coming to the decision about exactly where we will do our next drilling campaign to, again, deliver samples to the inside of the rover. As we've been going on, you have these periods of fairly quiet because you're trying to get somewhere. You're driving, really trying to discipline yourself to drive. Not, somebody said put blinders on, but every once in a while you stop.
Now, how far are you driving? How are you driving? Is it a joystick? Is it what is it?
It's not a joystick. It's basically a whole bunch of computer code. So what the scientists do is that they come in each day. Pretty much, there's kind of a disconnect in that this runs on Mars time, which is a day is 24 hours and roughly 40 minutes. We staff on Earth time. And so it works for a while, but you start getting disconnected. So it gets complicated. But basically, Each day you'll get pictures like this down, you get all these images down, and you'll say, okay, what do I want to do tomorrow? And then the scientists will build a plan, and the plan can go on 30, 40, 50 lines of information. And then we do what I like to think of as sending it to the engineers who turns all that information into zeros and ones. And then those zeros and ones get transmitted to the rover right at the last moment. We all go to bed, and then the rover is on completely autonomous, and it does what we command it to do for the following day. When it finishes that, stops, sends back the information, and then we start over.
So Curiosity is really living on Mars one day at a time, which is really quite remarkable considering all the time it's taken to get there, all the extraordinarily difficult planning, but it's really based upon what it learns one day. It sets the agenda for the next day.
That's right, and there's really nothing more exciting than that, right? I mean, if every day you're finding something new, it doesn't matter what you're doing, whether you're doing rover on Mars or doing whatever you're doing on Earth, if every day you're finding something new, it's always exciting.
So what are the challenges, what are the impediments, and what are the medium-term goals right now? I know there are some impediments that this rover is starting to face, and that's why we have this tire here.
This is a 1-to-1 scale model of the wheel, and so what has happened, and one of the reasons why we've slowed down is that it was always known that we would punch holes in the wheels. That was understood. But then they started to appear much more.
Now the wheel is a different substance.
That's right. It's an aluminum alloy. This is a plastic model. But, and so if you look down, you can see that there are these ribs. The ribs are really the structural strength of the wheel. And then there's aluminum metal plating in between, which helps distribute the forces, so it's actually valuable. But you can punch all kinds of holes in this, and it's not it's worrisome, but it's not a huge deal until you start breaking the ribs. That's when it becomes problematical. But we were putting holes in this much faster than we thought, and so a plan has been devised to mitigate that. And the two things that we do is, one, we drive backwards, and the way it was described to me by the engineers is that it's the difference between taking a wheelbarrow and pushing it over a curb versus taking your wheelie bag and pulling it over the curb. And that's kind of the difference in what's happening. Also, when you drive forwards, you punch holes in the front four wheels, and this just has to do with the geometry. When you drive backwards, you're only punching holes in the back two wheels. And the other thing that we're doing, which is also very important, is that we've changed where we drive. We used to drive the fastest we could, go across all the rocks, anything at all. But the rocks, it just turned out to be much sharper, much firmer in place than we expected. And so we're sort of pushing these holes in. So the idea now is to drop down off the hard rocks into these little valleys where it's sandier and softer, and they put much less wear on the wheel. But two problems with that. One is that it's a longer route. You're driving longer to get to where you want to go. The other is that the geology is so much more interesting that it's really hard not to stop.
And these are not rocks that you can kick aside.
No.
These are almost outcroppings.
If the rocks shift around a bit, if they move, then they'll just push out of the way and there wouldn't be a problem. And it was unexpected. The geological terrain we're on just and this is what happens. I mean, you're doing exploration, and you get something you weren't expecting, and you have to deal with it. And so this is the way they're dealing with it. And it turns out that the rate of damage has just really dropped a lot, and so we're pretty confident that we'll be fine.
So Curiosity is on its way slowly to Mount Sharp.
To Mount Sharp,
which is where the good stuff, best stuff, is supposed to be.
It's supposed to be, although I think it will struggle to compete with what we've already found, shall I say. But it is interesting. And it is the reason why we went. So we have to drive, again, as the crow flies, about 4 kilometers or so to the southwest, and probably more like 6 or 7 kilometers of true driving. And then once we get there, we enter into Mount Sharp. And Mount Sharp is a spectacular feature. It's 5.5 kilometers high, which, to give you a sense of scale, is higher than Mount Rainier. It's unlikely that Curiosity will find its way all the way to the top, but this geological transition between these clay-rich settings where we think it was a warm and wet setting up into these sulfates where we think Mars had dried out mostly takes place in the lower kilometer. So we're very confident we'll get to that, and we'll be able to explore that and evaluate that, and we should start getting results within about a year's time or so.
And try to, again, find those rocks which would have been havens for.
What we're looking for is evidence for microbial life, and the kind of life that we think is most likely, and the kind of life that we feel would have been appropriate for the work that we did at Yellowknife Bay, is some kind of a rock-eating life, microbial life. We're used to thinking of plants and animals, and but for microbes, they have evolved on Earth into many, many different ways of both getting their carbon to grow and the energy to allow them to do that. And the type of life that we're probably looking at is something called an autotroph. So it's probably getting its carbon from carbon dioxide, not unlike plants on Earth.
Pulling it in.
And pulling it in. And then the energy source, again, for microbial things on Earth, we're used to usually thinking of photosynthesis, right? It gets the energy from the sun. The feeling is that's probably not the case on Mars. That's something that would evolve later and probably did on Earth. But what we're looking for are other energy sources. And on Earth, there are things that we don't usually think about and don't hear so much about, but there are chemical reactions that take place within rocks that will also allow for energy. And organisms have figured out how to use that energy to allow them to metabolize and allow them to extract that carbon and grow.
And this is microbial life.
This is all microbial.
And is this a vestige of life once upon a time?
The thing about life is that it's extremely good at evolving into all kinds of environments. We can go to the most extreme places on Earth and we can find life.
Deep, deep, deep in the sea?
Which are deep in the oceans, in mines that have acidity of 0. I mean, you can go into deep caves, you can go into the subsurface. Life evolves into everything. But most people think that life probably originated in something much more benign, something more gentle. What Darwin, or people, I think Darwin may have actually called it the warm little pond. And so early on Mars history, just like early on Earth history, these kinds of microbial organisms, you know, we know about them on Earth. We have pretty good evidence that they were present. And the times are about the same, right? We're looking at rocks here that are roughly 3.5 billion years, and that's roughly when we have fossil evidence on Earth.
So let's say we find it. Mm-hmm. The question is, then what?
Well, I think beyond just the excitement of that, I think we would have to reevaluate our position, certainly in our solar system, if not in the universe, and it will have to make us change. If you think back to what the theory of evolution did to the way that humans think about everything, it was pretty profound. And my suspicion is that if we were to demonstrate that life originated and took hold on another planet so close by, it would suggest that at least that level of life, maybe not intelligent life, but some level of microbial life may not be uncommon. And as I said, my suspicion is that would have a profound influence on the way we think philosophically and otherwise. Yeah.
Well, we're going to open it up to questions right now because I'm sure many people have some. This has just been fascinating. So, yes, sir.
I have a two-part question. First, how do you feel about a manned mission to Mars? Okay, how exciting, how valuable. And the second question I have to ask you, though, but I have to find out if your wife is here. Is she here?
She's here.
So the second question is, how would you like to go?
Right. So the problem, I mean, human space flight is great, but these guys are like trivial expenses compared to what it would cost to put out humans. I mean, the costs just blow out amazingly.
What would be the range of cost, you think?
Well, these missions are, like one to, depending on, this is like about a $2 billion mission. I would think to put a human on Mars, you're looking at hundreds of billions. And the way that we would do it is sort of all being discussed sort of as we speak. And there's some private enterprise that are starting to think about doing it. There's a group in Europe that's trying to put together funding to put humans. Initially, we would probably put them into orbit and try that. One of the current ideas is that you don't send people to bring them back. You send them permanently, and it's like going to the New World.
How long will the trip be?
Depending on how you decide to do it. These guys take typically 7 to 9 months to get there, but to lift things off Mars and bring them back to Earth, it would take enormous resources. And so, if you wanted to do that, you'd have to take those resources with you, or you'd have to find them and engineer them there. Possible, but that's challenging. So I think that the chances are that if we were to do that, it would be exciting, and I think it would, but it's a commitment of enormous scale, because not only the cost of doing it, but then you're going to have people there and you have to take care of them. And that's also a huge commitment.
So would you like to go, be on the first mission?
I'm told that there is no shortage of people that would be more than happy to go ahead of me. I gather that there's literally hundreds and hundreds of people who have signed up as being willing to go.
Very diplomatic answer, by the way. Thank you.
I'm glad that you're not asking my wife.
Yes.
On any of the missions, have they found anything interesting about the types of elements that they found in the soil or the atmosphere?
What's been really noticeable about it is it's very rich in sulfur and to some degree chlorine. And sulfur is an element that we find enriched on the surfaces of many planets, but on Earth it's not so enriched. And one of my friends calls it it's the Las Vegas effect, in that on Mars, because there's no plate tectonics, there's no way of returning things to the interior of Mars like there is on Earth. And we have subduction and we move things, and on Mars there's not that. So he calls it the Las Vegas effect because he says whatever gets to the surface stays at the surface. and so on Mars and Mercury and Venus and other bodies that don't have this plate tectonic process, these things get brought out to the surface during volcanic eruptions and whatnot, and there's no mechanism for tying them up and then either putting them back into the depths of the planet or turning them into rocks that then get sequestered away somewhere else.
Hi, I have a question about the moving stones. There's such phenomenon on the Earth when there's stones were moving for tens of miles and there's no specific explanation for that.
Right.
And I know that Curiosity actually took the photo of few moving stones
Right.
on the Mars.
Yeah.
So what's exactly could be a reason for
I
that?
think that was the Opportunity. Is that the one that was Opportunity? They found the thing was there and then it wasn't there. So what they think happened, it's those of us who have had stones come up onto our windscreen are well aware of. They think what happened is that in the case of Opportunity, the wheel just went over this edge of a rock and it flicked it, in front of it. Yeah. And there was some guy, actually I think he filed a lawsuit to try to make us go back and study it because they thought it meant life or something. But we did. We went back and we looked at it very carefully, and you could actually find the divot. You could actually reconstruct what we think happened, and we think that's really what it was.
Okay, thank you very much.
You're welcome.
Periodically, rocks from Earth will get to Mars and vice versa. If we found life on Mars, what do you think that the possibility that's related to life on Earth?
It's being, and vice versa has been suggested. So far, we don't have any good evidence that material from Earth has gotten to Mars. We don't know that yet. But there is a collection of meteorites on Earth, roughly, I think it's up to like 60 or 70 now, that we are very confident originate from Mars. So the idea is that you have a meteorite impact hits Mars, and then the shock wave is such that it pushes material up and gets into orbit, and over time it crosses Earth's orbit and hits us like as a meteorite. And in fact, what got the whole modern Mars exploration program going was this famous Martian meteorite where people thought they found evidence for microbial life, fossil life. That, I think now is, not many people buy that. Some do, but not many. But it led to the idea that you could salt one planet could salt another. I mean, it certainly demonstrates that you can move material from one planet to another, and there's no question about that. We now, I mean, if we were to find material, if you could actually find biological material, I don't know if you'd ever get to DNA. I'm not sure whether you could ever really convince yourself that they were related or not, but it's certainly possible. Certainly possible.
Okay, so a 16-year-old boy just took a trip to Hawaii in the wheel well of a jetliner.
I heard that, yeah.
What are the chances that microbes from Earth are in your vehicles?
Right. There is a chance, there is a real chance that there are. There is a whole subculture of planetary exploration called planetary protection. And the role of planetary protection is to both ensure that microbes from Earth don't go to Mars, and that microbes from Mars don't come back to Earth. The second isn't so much of a problem anymore. We're trying to get stuff back. But when it comes back, we will take very careful care of it. But stuff getting to Mars is a worry. So, for example, If you propose a landing site where there is even a slim chance of liquid water being present today, you have to sterilize the vehicle, and that would probably almost double the cost. So you don't go to places like that.
Fascinating, fascinating. We've heard talk about a twin planet 500 million light years away and a moon of one of the planets in our solar system potentially also being hospitable to life. So there are other places that are going to be sources of perhaps even greater fascination than Mars. But Mars has for so long been an object of fascination and, as you suggest, might hold a real paradigm shifting view of who we are in the universe.
Indeed, indeed.
Please join me in thanking Scott McLennan and thanking the Sag Harbor Yacht Club for a fascinating evening. Have a beer? Good toast. Thank you very much.